Great.
Okay. Hi, everyone. I'm Karunya, and I'm a postdoc at Virginia Tech. And today I'm going to be talking about breaking symmetries in adaptive quantum simulations of the lattice Schwinger model. So an adaptive quantum simulation basically involves using the adapt VQE algorithm to prepare a desired state of a system. In particular, the adapt VQE algorithm works by iteratively constructing an ansatz in order to prepare the ground state. So here we're going to focus on preparing ground states of systems. And the way it works is by starting with an initial reference state. Now, there's an important input that goes into the problem, which is called the operator pool, which you can think of as a set of building blocks with which you would construct your wave function ansatz. So what the algorithm does is, at each step, it tests out the capability of each operator in the pool to lower the energy of the system. It chooses the one that has the greatest capability of lowering, that lowers the energy by the largest amount, adds that to the ansatz with its own variational coefficient, and then optimizes all the coefficients. And this process is carried out repeatedly until one has hopefully reached the global minimum of the cost function. Now, let's focus on the image on the right for now. So the blue shaded region represents the Hilbert space of the problem. The yellow shaded region represents a symmetry subspace in which the symmetries of the problem are preserved. The blue dot is our initial reference state, and the green star is the target state of the system. Now, conventional wisdom dictates that one should preserve symmetries in our simulations. That is, preserve the symmetry both in the reference state as well as for adapt VQE in the operator pool. But the question that I want to ask is this quantum resource efficient? That is, can we always come up with quantum circuits that that efficiently use resources while also preserving the symmetries of the problem? Now, there are examples in which the adapt VQE algorithm, for example, breaks the symmetries of the system along the way, but regains them at the end and is able to accurately prepare the ground state. So the question that I want to ask is, what is the effect of relaxing symmetries in these simulations? And moreover, do all symmetries, for example, particle number conservation, time reversal symmetry, translation invariance, etc., behave similarly? Or is the algorithm more sensitive to breaking particular symmetries? So the model that I'm going to focus on today is the lattice Schwinger model. Now, this model it describes quantum electrodynamics in 1+1 dimensions. While it is a sort of toy model, the hope is that one can use the methods developed for this model to study gauge theories in higher dimensions. Now, the model is defined on a special kind of lattice, which is called a staggered lattice. So you can think of starting off with physical sites at the top of the picture of the figure, and each physical site consists of a pair of fermion and antifermion sites, and these are represented in the figure below, and these sites are linked by gauge fields. Now, however, in our simulations, we do integrate out the gauge fields. And in a Hamiltonian, you can think of the first term as representing the kinetic energy in the system, the second term as representing the mass in the system, and the last term as representing the particle coupling in the system. Now, how do we go about running adapt VQE on this model? Well, we need to choose an operator pool to run our simulations. Now, the symmetries of the model suggest using operators that are charge neutral, symmetric under charge conservation and parity, as well as time reversal invariant. Now, there was a very nice work that came out last year in which the authors developed a method based on AdaptVQE to run, to prepare the ground states of very large system sizes of this model. And in their work, the authors used an operator pool that used translation invariant bulk or volume type operators, as well as surface or boundary type operators with support only near the boundaries. And these are depicted in the figure on the right. Now, therefore, the symmetries of the problem consist of coordinate or translation invariance. Now, note that this is up to the boundaries of the system, because our model does have open boundary conditions. Another symmetry is the charge conservation in the system. And then we also have the time reversal symmetry in the system. Therefore, what we do in our work is to systematically relax each of these symmetries in our simulations and look at the result after applying AdaptVQE with each of these pools on our final results. So the symmetries that I'm going to relax here are the coordinate invariance lambda, the charge conservation C, and then there's another property that I consider, which is the property of retaining the Jordan-Wigner strings that come from transforming from a second quantized basis to the qubit basis. So in the figure and in the diagram, I'm depicting the way in which we relax these symmetries. So we start off with a parent pool, which preserves all of the symmetries, and then we relax them step by step in order to obtain pools that, for example, relax the translation symmetry, relax the charge conservation, and finally, at the bottom, I have a pool that doesn't preserve any of the symmetries of the system and has broken down the parent pool into individual pieces. So let's look at the results. So the first way in which I quantify the effect of relaxing these symmetries is by looking at the final energy accuracy that's obtained by the algorithm. So I'm going to be looking at the energy density error as we run the algorithm. So first of all, we notice that the parent pool, which is red, and the yellow pool, which relaxes the charge conservation, both are able to achieve accurate energies. Next, on the other hand, we find that two other translation invariant pools, which in addition to relaxing the charge conservation as earlier, also relax the property of the Z. So let's look at the orange and purple curves for now. So these are translation invariant operator pools, but we can see that they are not able to achieve a good final energy accuracy. So they don't perform very well. Now let's think about the charge conservation next. So I want you to look at the dark blue curve versus the pink curve. So this consists of a pair of pools that preserve the charge conservation, which is the dark blue, and the pink, which relaxes the charge conservation. So we can see that both of them achieve very similar energy errors at the end, but they take a different number of iterations to converge to similar energies. Similarly, you could look at the light green versus the light blue. Now, these are a pair of pools in which the light green preserves the charge conservation and the light blue breaks it. But again, we can see that these two pools both achieve similar energy accuracies with slightly differing number of iterations. And overall, these are our results for all the pools. So we can see I guess overall, that the translation invariant pools struggle or take the most number of steps to converge if they do converge. We also see that retaining the Z strings in our operator pool turns out to be beneficial, and those pools lead to more accurate energies. So next, let me talk about quantum resources, because this is part of how I motivated the problem. So let's look at the resource usage by different pools. So the assumption here is that there's a full connectivity between the qubits, and we use the Qiskit transpiler in order to obtain the CNOT depths. So overall, we find that the light green and light blue pools achieve the greatest accuracy, although the red and yellow also achieve a similar accuracy with more CNOTs. And regarding the charge conservation, we see that, look at the dark blue and pink pair, as well as the light green and light blue pair. We can see that even though those pairs of pools relax the charge conservation, one of them relaxes the charge conservation, we find overall that there's a similar CNOT depth and energy accuracy that's achieved by those pools. So let me get to my conclusions. So in conclusion, we found that breaking the translation symmetry in the problem appears to be favored, which is an unexpected result, given that we do have a lattice model that does have the translation symmetry. Now, one could say that the open boundary conditions in our problem could favor relaxing translation invariance. However, as we increase the size of the system, we expect the boundaries to become less important. But we do find that the pools, the coordinate invariant pools, perform similarly for all system sizes that we've looked at. So this leads to the question of whether this leads to the question of whether we can indeed make such a conclusion about the translation symmetry. And so currently, what we're doing is running experiments for a fermionic model on a periodic lattice, which has periodic boundary conditions. And then regarding the charge conservation, we find that there is no benefit to relaxing the charge conservation. Sorry, I'm out of time, but yeah, I don't think there's, sorry. If anybody has questions, I'm happy to take them. Or maybe outside.
Yeah, I think we don't have time for questions, unfortunately.